Hi, Lecture 15. In this lecture now we're moving on from the performance issues, performance program, to the issue of robustness. We're looking at now the control of systems and looking at robustness properties. So here we are in our list of topics. We're talking now about the robustness program. So that's where we're at. And we've seen that the basic control structure looks something like this. You have your plant. Here's our computer that includes our controllers, the digital to analog, analog to digital. Okay, so our controller, again, is a 2 degree of freedom controller. But the real problem that we have actually has some things in it that make this whole process more complicated. We've talked a bit about saturation, and that's one of the reasons, the saturation is one of the reasons why we need to incorporate a control magnitude constraint in our performance program. So we actually can take this into account somewhat by our performance program. So it turns out that it actually can wield its ugly head in other settings, and particularly this robustness setting. So that's something we're going to have to take a look, keep our eye on. Some other things that we've got going on here is we have, so here is our output signal, the output of our plant, and we're measuring it, but in the process we actually get sensor noise that comes out. Okay, so that's another signal that actually enters the system. In our analog to digital converter and digital to analog converter, I have represented these input signals that are a result of what's called quantization. Quantization is the fact that when you convert an analog signal to a digital signal, you convert it to a particular number of bits, and therefore, so the actual signal can be, for example, any value between, say, plus and minus 10 volts, right? But that is broken up into 2 to the n values, and the signal then is only one of those values. It's not just any number in there. And so, if the actual value is in between 2 values, there's an error. There's an error associated with that, and that error can be represented by a noise or a signal, external signal. So it's like this is an exact sampling, and then you have a signal that's being added that is like noise, and we'll see how it looks like noise here in just a little bit. So we also have here, instead of P of S, we have PA of S. That's our actual plant. Okay, so remember when we did system identification, we got a model, and sometimes the model was good, sometimes maybe not so good, but our actual, we know with system identification that our actual and what we got in system identification might not match exactly. So we have an actual plant, and then we have the plant that we use to design the controller. We'll call that the nominal plant. And so we have a number of imperfections in our system, or non-idealities. This is not an ideal situation, but it's a real situation. So we need to take into account a lot of the real problems that arise in the control problem. So robustness is needed, and I talk about robustness in 2 types. Type 1 is against noises. Type 2 is against modeling uncertainty. So we saw where noises could arise in a number of cases, and we also have modeling uncertainty that can arise. So in terms of quantization, I talked about quantization in the A to D converter. So here I've got a 12-bit A to D converter represented. Here is a signal that's being used, and I'm going to plot both the signal and the quantized signal together. And when I overlay them, they're just right on top of one another. So you can't really, it's not that easy to see it for a 12-bit converter. But if we zoom in, notice this is 10 to the minus 3. We can see that we get a signal. If I take the difference between these 2 signals, then we get a signal that it's a discrete time signal, and it is not constant. It is not 0. Okay, so there is an error, and it may be small based on the resolution of the converter, but it is there. Okay, it is there, and it has statistics that act often very much like a noise. Okay, so a question is then, what is noise? What kind of a signal is it? how does it affect systems? How can we eliminate it? So this is the bottom line. How can we eliminate it? But we need to have some understanding of it in order to be able to work with it. And I'm going to just cover this very briefly. I'm not going to talk about the whole depth of random processes and stochastic processes and so forth. It's a very complicated subject. I'm going to cover it at a very brief level. So when we talk about noise, we're basically talking about a signal that is additive, white, and Gaussian. And if you take a class in stochastic processes, this will make sense to you. So AWGN is just the initials we use. So these are assumptions that we make. And you can have other kinds of noises. You can have multiplicative noises instead of additive. You can have colored noise instead of white noise. You can have Gauss. You can have other distributions like Rissian, a Rice noise process instead of Gaussian. So there are other types of noise models that can be considered. This is a specific noise model that is very commonly used. Okay. Now, the important thing about noise is that the values are unpredictable. You don't know what it's going to be at any given time, and they generally don't follow any particular pattern. So that is, if it's white, it doesn't follow any pattern. If it's color, it can actually follow a pattern. So these are called stochastic processes, and they need to be analyzed using probability and statistics. And when a noise is introduced into a system, all the signals within the loop become stochastic. They can become random. So it can really create a lot of headache for the system that has noise in it. All right. Now the mean of the signal. So we're going to talk just a little bit about the statistics. The mean of the signal is the average value. So if you look at n values of the signal, W, if you add them up and divide by n, that's the mean. That's kind of like the average. That's a pretty standard kind of definition. The variance of a signal is the mean of the square of the difference between the signal and the mean. So what that means is I take W, which is my signal, I subtract the mean, which I've computed up here. Okay, so that's just a number. Once I've done this computation, this is just a number. And now I take the difference between W and the mean. So this, you can go through and show that this number inside of here is a random. So even though this is just a constant, this is a random sequence that has zero mean. The mean of this quantity is 0. So anyway, you take this and you square those values, and then you average those. Okay, so that's what the rest of this is. And that's called the variance. Okay, sometimes they'll have 1 over n minus 1. Sometimes you'll see that definition. So there are different definitions. An additive white Gaussian signal is defined, its probability distribution is defined by the mean and the variance. And so that's one of the reasons why we work with Gaussian, is because it's actually one of the simplest to use. And so we start simple. And yet it's very rich. It's a very rich type of noise signal. So, and actually you can show using something called the central limit theorem that a lot of random processes, random things, follow a stochastic process, Gaussian distribution. So anyway, there's a lot of good reasons for using it. Now, of course, if you know that your noise is not Gaussian, then well, that's another issue. You might want to use a different approach than what we're going to take here. All right. So, all right, now let's talk a little bit about what happens to operations when we have noises. So here I have W1 and W2. W1 is normally, so the N here stands for normally distributed. A normal distribution is the same as a Gaussian distribution. So that's what this N is. And what this is saying is this is a random variable with mean mu1 and variance sigma 1. Okay. This is another random process, normally distributed with mean mu2 and variance sigma 2. Don't let the Greek letters throw you. These are just numbers, okay? And they use the symbols mu and sigma, Greek letters. Don't let that Greekify you. Don't let it wipe you out here, okay? Just stay with me. So when I take these two signals, these two random signals, add them together, I get a signal that is normally distributed. And guess what? The mean of the mean of this signal is the mean of the individual signals. Okay? And the variance, well, the variance is not the sum of the two variances. Okay? If the two signals are uncorrelated, then the variance is the sum of the two variances. But sorry, I'm making assumptions that are just not right. So let me back up a little bit. Here, normal distribution with mean, and this is not variance, this is the square root of the variance. The variance is actually this quantity squared. So this quantity, which is the square root of the variance, is called the standard deviation. So we will often write it in terms of its mean and standard deviation, not mean and variance. So sorry about that. I wasn't being precise here. So the standard deviation of two signals, if they are uncorrelated, is the sum of the standard deviations. And what we mean by uncorrelated, you can think of it as being completely unrelated. Okay, if so, correlated means there's some kind of connection between the two random variables. Uncorrelated means that they're not at all related. They're completely independent processes that are creating those noise. Now that we have noise coming into a gain block, just a constant gain, then the statistics give us that the mean of this signal is the mean of the incoming signal scaled, and the standard deviation is also scaled. Okay, scaled by the value, by whatever value it is that we're multiplying by. So basically, scaling a noise basically scales both its mean and its variance. Okay, just scales the whole thing. So that's what happens when we scale it. Now, what happens if we put a noise into a transfer function? Okay, not just a gain, but a frequency-dependent gain, which is one way of looking at a transfer function. Well, you can go through and show that, again, the variance is given by this expression, the variance of W1. You can show that the variance of the output is related by this inequality. It's less than or equal to the sum of the squares of the Q transform of the transfer function, the inverse Q transform. So this is actually what we call the impulse response. And so you can show that the variance of the output is less than or equal to the square of the impulse response elements summed from 0 to infinity. Incidentally, if your system is stable, this summation from 0 to infinity will always converge to something. It'll be finite. So you can actually go through and prove that. So that's important. And so notice that we don't know exactly what the variance is, but we know that the variance is going to be less than or equal to this quantity. It's related to the variance of the incoming signal here, and it's related to the transfer function here. Okay, so we have that. And in general, so if it's a stable system, this is what we'll have. If it's a stable system, then in general, the notice here I have 0 mean. It turns out that if this is a stable system, the mean of this will also be 0. Okay, so we don't have to work. So we will often work with 0 mean signals because they simplify. And it turns out a lot of random noises really are 0 mean. That is, they do not have a DC component to them. So you can think of the mean of a random signal as being its DC component. And so it's very common to have noises that do not have a DC component to them. All right, so how does the noise affect a system? So we're going to assume for now that our noise we're going to be working with is sensor noise. We talked about how you can have quantization noise, but generally speaking, if you have an accurate or several, quite a few bits of your converter, like 12 bits or 14 bits or whatever, the quantization noise is not going to be a significant contribution in the system. It is there and it will affect things, but it's not huge. It doesn't generally will not have a huge impact. However, the sensor noise generally will. And again, we're going to assume the sensor noise is zero mean. So the reason it can be a problem is that the sensor noise could actually be amplified by the controller, and the resulting signal exceeds the saturation limit. So we design a controller to meet the performance program that has saturation, or that takes into account control magnitude constraints. But now you have another signal coming in that's going to mess up all of the signals, and in particular, it may throw the saturation may throw the whole thing off. Okay, so the transfer function from the sensor noise to the control signal. So PWU is a transfer function from the noise to the control signal. So that's from this signal to this signal. And again, this is here, but in the process of doing this, we're going to assume that the signals are not being saturated at this point. So we could think of it as here or here. Okay, so that's basically what we're looking at when we think of the transfer function from W to U. So it's given by this expression, which is reduced down to this. And again, because this bottom equation satisfies the Diophantine equation, then it comes down to this. Again, it's a polynomial. And in this case, notice it's dependent upon n2, not n1. So that is, n2 is independent of v1. It's dependent on v2. So in order to work with this transfer function, we need to adjust v2, not v1. So we didn't see v2 coming in any of the performance issues that we looked at, but it definitely comes out here in this robustness problem. So if we now take the vectorized form of our transfer function, which basically is the impulse response of our transfer function. Notice in this case, it's a polynomial, which means we can actually get a finite. We don't have to sum all the way out to infinity. We get a finite sum, and we can actually express it this way. Again, we have a vector, and then we have this expanded matrix times our unknown v2. So you can actually write it out, the transfer function from the sensor noise to the control signal. You can actually write it out this way in a vectorized form. So what does this buy us? Well, so remember that the variance of this signal, so remember now we're looking at the input being W and the output of this transfer function being U. This is going to be of zero noise with standard deviation sigma W. This is going to be normally distributed with mean 0 and standard deviation U. And we know now that the variance of U, this signal, is less than or equal to this quantity times this variance. Okay, and this signal here, which is summed up from 0 to infinity, can actually be written this way. It's a finite sum, and it can be written as this vector transpose times the vector, which can be written this way. And we've seen this kind of thing before. And so now we want to find a v2 associated with this. Okay. Now, when the sensor noise is present, it's desirable to make the variance of U as small as possible. In other words, the impact of that noise on the control signal, we want to make it as small as possible. That is, the control is impervious to the noise, and so that's what we'd like to do. Now, since the variance of W is outside of our control, so that it's noise, we can't control that. It's coming in, and it's part of the sensor, and perhaps we can control it somewhat by choosing a better sensor. But at some point, you have a sensor, and it has some noise, and you're stuck with that noise, and you don't have any control over what that noise level is. And but it's a fixed value. So since that is fixed, if we want to reduce the impact of the sensor noise on the control signal, then we need to make the transfer function PWU as small as possible. That process is called attenuation. Now, in this case, we don't have any hard constraints, and so we can choose the global optimum. The global optimum is the least square solution. So we want to make this small, and this quantity is given by this expression. The least square solution to this problem of minimizing this is using the pseudo inverse. It's given by minus G1 pseudo inverse times G0. So we have an exact solution. Let's look at an example of what this looks like. So here's our system. We're going to sample it with sampling period 0.1. We're going to find N1 to satisfy a performance program so the system settles in 0.5 seconds with control strategy less than 5, minimum control energy. This is the N1 that we get in that case. This N2 and DC are the minimum order solutions to our Diophantine equation. And we can simulate this system using a Simulink diagram like we've used before. Notice now we have saturation coming in, we have band limited noise coming in, so we have a number of extra signals. And here I'm actually plotting the difference between the output of my controller and the output of my saturation. So you can see where saturation occurs. Okay. And so the rest of the control Simulink diagram is the same as what we've seen before. Here are the results. Okay, now what's going on here? So I have the simulation for 3 values of variance of the control signal. I mean the noise. Okay, so this crimson signal, you can see underneath you have low overshoot on the output. It settles, basically in 0.5 seconds like we've asked it to. And the control signal, well, actually, we're not looking at the control signal here. No, actually, this is the control signal in here. So that should say U of t. And so this control signal, you can see it does its thing, and then it settles. Okay. Now, here, I've simulated this with small noise, variance equal 10 to the minus 12. That's pretty small. If we now look at increasing the noise from 10 to the minus 12 to 8 times 10 to the minus 7, so noise is quite a bit bigger than this, you get this kind of response. Okay, so this is Y of t. This is the output of the system itself. Here's the output of the system with the noise. That is this is what the sensor is actually looking at. Okay, and you can see it's got noise on it. This one is pretty much noiseless. Okay, this has got noise, and so you can see when I've added noise now, the green is the response that I get for this level of noise. So it's still it's not a lot of noise. 10 to the minus 7, that's still pretty small, but you can see it has enough noise that it's causing the system to not settle. It meanders. Okay, it meanders. It's not settled. So this kind of meandering is very common when you have noise entering a system. The output meanders. Okay, so the green, if you look at the green control signal, you can see the control signal actually does pretty well in this initial part, and then every now and then it goes outside of the saturation bounds. Okay, so that's what's going on over here. So finally, we increase the noise from 8 times 10 to the minus 7 to 6 times 10 to the minus 6. So that's not even a factor of 10. It's a factor less than 10. So this is like a factor of 10 to the 5, which is like 10,000. So the noise difference between these two is 10,000. The noise difference between these is less than 10. And so, and you can see now, the red is the actual output. Notice that it's noiseless. Here is the noisy version. You can see it's got significant noise on it. And you can see the system's blowing up. If you look at the control signal, for example, the control signal is definitely outside of its bounds, and it's blowing up. The system is blowing up. So the same system, if you increase the noise large enough, you can make the system blow up. That's the takeaway from this slide. So notice that we use the minimum order solution on N2. So what happens now if we introduce a V2 to reduce the effect of the noise? So remember, we have now an unconstrained optimization problem. We can choose the global minimum for this. So we're going to try this, and we're going to use V2 has degree of 10. So it's a significant increase. And when we do that, here's our N2 and DC. You can see now these are This is the 13th order polynomial. These are both 13th order polynomials. N1 remains unchanged because that's not part of this Diophantine equation. And so you can see that the controller polynomials have increased. And now let's look at the response of the system to the response of the system now when we use these controller polynomials. So here's what we get. Again, when the variance is small, we get a nice performance, small overshoot, and so forth. Okay, less than 5% overshoot. And here's the noisy version. You can see it's not much noise. Here's the control signal. Okay, and so here's the control signal. It's doing its thing. So when we increase the noise up again to 6 times 10 to the minus 6, notice that we get some meandering. You can see here the signal with the noise. So the difference between this signal and this signal is this one does not have the noise. This one does have the noise. So remember that noise is actually in the sensor. It's not in the system. So this is the actual output of the system. This is the output of the system that we would measure. Okay, so that's what we see. And as you can see, it meanders. It's still meandering a little bit. It doesn't settle exactly, and that's not something we can actually get rid of. Okay, we can't completely get rid of it. But notice that the system meanders, but it meanders less than it did before. And when we look at the control signal, so remember we designed the polynomial n2 in order to minimize the impact of the noise on the control signal. And so you can see the green is the control signal, and you can see it's very close to the crimson. It's not exactly the crimson. It's still meandering, but it stays very close to the crimson. And now the third case here is when the variance is 2 times 10 to the 4. So this is not 10 times this. This is more like so this is 10 to the minus 4. This is 10 to the minus 6. So this is like 30 times the noise of that. It's not 10 times. It's like 30 times. And so you can see the noise is quite significant. Okay, it's quite significant. And you can see the output of the system is definitely meandering a lot more. Definitely meandering. But what we noticed, so notice that this noise is actually greater than the noise we had in the minimum order case for N2. It's significantly larger, and yet the system does not go unstable. In fact, if you look at the control magnitude still stays between plus and minus 5. Okay, so we see that even with significant noise levels, the system still doesn't blow up. It meanders, but it doesn't blow up. Okay, so we have effectively stabilized the system, but it was at the expense of using a more complicated controller. Right? Here's the controller here are the controller polynomials. They're definitely more complicated. So that's what we have. All right, so that's type 1 robustness. Type 2 robustness is robustness due to modeling uncertainty. Okay, so for now we're going to set aside the notion of the existence of the noise, and we're going to look at a different problem altogether, the problem of uncertainty. So here we have what's called our nominal plant. This is the plant that we think we have, but there's some uncertainty associated with that. Okay, so our actual plant has uncertainty in it. All right, so we want to design our controller in this problem. So when we actually design our controller, we're going to assume this kind of a situation where we have P subscript H. But now, with the uncertainty, we have P subscript H and Px. Px is our unknown, and we can go through and define Px this way in terms of P delta, or P delta is another way of expressing the uncertainty. We looked at that once before. So Px can be written this way in terms of P delta, but now we have the actual open loop plant. So the actual open loop plant includes all of this stuff, okay, involving P delta. So we can go through and solve for P delta from this expression, and this is what we get. Now it's like, why would we write Px this way? Well, it turns out we could have started with P delta instead and looked at P delta as the normalized transfer function between the actual pH and the nominal pH. So the actual is what we actually have. The nominal is what we have available to use for designing. Okay, so this is known, this is unknown. Okay, so if we take the difference between the known and the unknown and divide by the unknown, this is like a % difference in the unknown. Okay, so or another way of saying it, it's normalized. So the reason why we write it in terms of P delta is because P delta has a natural interpretation as being the % difference or the % error between what we know and what we don't know. Okay, so that's one of the reasons why we use this. Okay, since we don't know P delta, then we don't know the actual transfer function. And so this form of the uncertainty is like the % difference between the actual and the nominal. The nominal model pH and the actual model pHa are given in discrete time. And so we're going to use the discrete time to do this. The nominal model could have been obtained also by a system identification. And so you remember when we did system identification, if there was noise present, we may not get a good fit. If we don't choose our model order correctly, the two models might not even be of the same order. Okay, so that's something to think about. Okay. Now, using the nominal model, this is our closed loop transfer function. This is the transfer function from R to Y. Okay, so this is our transfer function. Notice it involves C1 and C2. Using the same controller and the actual transfer function, this is our actual closed loop transfer function. Notice the controller is going to be the same, but the transfer function that we use here for the plant is different. Okay, so we can now define the % difference of this transfer function. So it's the actual minus the nominal divided by the actual. So here is the actual, here's the nominal, here's the actual. So this is what we get. We simplify it and it actually boils down to this. Okay, and so we can actually write this as a product of this times this. Now this we've actually seen before. That was what we called P delta. Okay, so the transfer function, the % difference in the transfer function between the actual and the nominal closed loop transfer functions can actually be expressed this way in terms of what we had called P delta and then this quantity here. So we can define, if we define S subscript H to be this quantity, then Y delta has the transfer function given by this. It's S subscript H. S here actually stands for something called the sensitivity function, which is very commonly used in control systems. Anyway, that's why we use the symbol S. The sensitivity function, and then we have the uncertainty associated with the original system. So this is what we have in terms of our SH. If we simplify this down, it comes out to be this quantity. So notice it depends upon DC, which again depends upon V2. And so we have that. Thus, in order to make the overall impact of the uncertainty small, we would want to make this transfer function small. This transfer function here, that's the uncertainty. We can't really change that. That is a function of our uncertainty. That's well, you can change this by getting a more accurate nominal model. Okay, but once at some point we're left with a nominal model, and there will generally be some error associated with that. Again, so to minimize the impact, once we choose a nominal model, then our uncertainty is fixed, even though it's still unknown. It's fixed. So this is fixed, and so in terms of minimizing or reducing the effect of the uncertainty, we would have this quantity here that we need to minimize. So we can't change this, but we can change that. So we want to make S subscript H as a transfer function small. So remember, S subscript H is given by this expression, which involves V2. And so to make this small, we can do similar to what we did with minimizing noise. So one way to talk about making this transfer function small is to look at the norm of that quantity. So we talked a little bit earlier about norms, a norm being like the size of something. And so the norm squared of the vectorized form of h. So remember, sh is a polynomial. So we can vectorize it, okay? And so one way of minimizing the transfer function or the size of this vector is to minimize the norm of it. And so one way of writing the norm of it is as this quantity transposed times itself, the vectorized form. So this is actually, in terms of systems, this is actually called the 2 norm of the system. And that's one way of defining this. So one way of making this small is to make this quantity small. Notice that this quantity is a function of v2. And so this has a least square solution. The least square solution involves basically choosing v2 to make all of this equal to 0, or as small as possible. That has a least square solution that's given by this expression. So if I call this quantity g2, so this is a vectorized form of h, of sh. This is g3. Okay, so if we want to minimize this quantity, we have a global optimum solution, which is the least squares solution, which is this quantity pseudo-inverse times that minus. Okay, and so we have a solution. Cool. I mean, once we have it set up to do this kind of, once all of our transfer functions end up being polynomials, that makes these calculations very straightforward. So notice I don't have any constraints on this. I just want to make this as small as possible. So we don't have to go through the quadratic program. We can do this directly using just a least squares, the global solution. So that's what we have. So now we have a way of addressing uncertainty in our modeling. And we've also talked about uncertainty associated with noise. So what happens now if we want to deal with both type 1 and type 2 problems? Okay, so we want to incorporate both types of robustness. That is, we want to minimize the impact of both sensor noise and modeling uncertainty. Well, the way we do that is we formed a combined cost and we minimize that. So our cost for the robustness is, again, it's a function of v2. We can write this way: beta of w uv 1 minus beta ws, where beta is a number between 0 and 1. Okay, here we go. So beta is between 0 and 1. And so again, if beta is equal to 0, then this term goes away, and this, we're only looking at ws. So that's the uncertainty. That's the uncertainty portion. So if we only have the problem of modeling uncertainty, then we can let beta equal 0, and we are just looking at modeling uncertainty. If we want to examine just the noise, so we assume we have a perfect model, then, and we just want to look at the minimize the impact of the noise, then we would let beta be equal to 1. Okay, so, or I can choose something anywhere between there to either emphasize the noise or emphasize the uncertainty. Okay, so so this is the noise issue. So we had G0, G1. Here we have the uncertainty, G2 and G3. And so we can now combine all of this together into an overall cost that takes into account both. Okay, and so you can think of beta being like a slider between, and that slides this quantity between the noise, handling noise, and handling uncertainty in it. And beta is like a number. So between 0 and 1, it will either choose, more noise or more uncertainty, depending on where you put it. Or you can weight them equally by making beta 1/2, in which case they're weighted equally. So this is a robustness program. And in this case, we don't have any constraints. We're just going to minimize. Okay. Well, so putting all this together, then we can actually put all of this together into a single cost, and we can write it out this way. So notice that we get this. If we now define G4 and G5, so notice that these depend upon beta, G0, G1, G2, G3, then we can write this cost this way in terms of this quadratic expression. And so now this expression has a global optimum, right? We don't have any other constraints to worry about. And so this problem now has a solution given by this, G4 and G5, which take into account G0, G1, G2, G, and G4. G0, 1, 2, and 3. And so, and beta, and the weighting. And so we now have a way of completely solving the robustness problem. So the robustness problem is actually a more complicated problem. Notice we had to go into stochastic processes. We had to talk about modeling of uncertainties. So there's actually some complicating things associated with that. We have made very specific assumptions. But notice in all of this, we end up with a solution that is much simpler than with the performance. In the performance, we had those constraints. We had to go to a quadratic program. Here, we don't have any of that. We have an exact solution to this. So let's look at an example, okay, that considers both. All right, so we're going to consider the system. We're going to consider the system that's given by this expression. Notice that this expression has a time delay in it, okay, and it's unstable. Okay. So we're going to sample with sample period t is equal to 0.1, and we get this expression for this discrete time model. This is our actual model. Now, we have used system identification on the system somehow. Don't say how, and we obtained this model. Okay, so you can see they're not identical. Okay, so not identical, and so there's obviously some modeling error associated with this. So notice the pole is not exactly the same. Okay, but this is what we obtained by doing system identification. We don't actually know this. Okay, we don't know this. Okay, in our design process. If we knew it, we would just design for this directly, and we'd be done with modeling uncertainty. But in our case, we obtained a model by system identification. So this is what we know, and we know that what we know is not perfect. And this is the actual. So we have actually a basis of comparison to see how does this whole process even work. So we're going to design, here's our performance program. We want to minimize the control energy subject to overshoot less than 5%, settling time less than 0.5, control magnitude less than 5. And here's our robustness program. We're going to weight between uncertainty and noise. We're going to, in this case, in our problem, our sensor actually has a noise, and here's the noise power, 10 to the minus 5. Okay, so we have noise, we have uncertainty, and now we're going to combine them together. So for this particular problem, here are minimum order solutions. Now, in general, we're going to have to notice that this value is greater than 5. That tells us automatically this minimum order solution is not going to work in terms of keeping our control magnitude less than 5. I can look at that and see control magnitude is not going to be less than 5. This is going to be a problem. So we can go through and use the quadratic program the quadratic program solver to give us solutions for the performance program. Okay, here is MATLAB code that we can use to solve this problem. So notice that in this case, I'm actually showing you explicitly how I set up the matrices to solve the performance program. So down at the bottom, we come up with quadprog that allows us to solve the quadratic program associated with this problem. Okay, and so this is what we have as the solution to the, in order to solve this. Here I'm letting m be 2, and so this is the number of steps to settle, and so forth. Okay, so this is the MATLAB code we use. It turns out we can find a solution given by this that solves the performance program. Okay, so next we use this code in MATLAB to solve the robustness program. Notice that I went to I used a fairly large order for the number of degrees of freedom for this. Resulting polynomials are of a large order. So I formed G0, G1, G2, G3, then G4 and G5. So here's the beta that we're working with. And so then I can just use, notice I'm using the backslash instead of the pseudo-inverse function. And when I'm all done, in this case, I'm actually doing the transpose, because this is actually going to be doing the transpose will make this into a polynomial, or into a row, the way we do polynomials. All right, next we come to our simulation diagram. So here we have added this for the control to see what's happening with the saturation. Now we're using the actual transfer function in our in this simulation. So our actual our transfer function has a numerator denominator that's the actual part, and then it has a time delay that's part of that. Okay, we have noise that's added, and so we have a bunch of stuff going on here. Okay, so this is the model that we had. When the robustness program is not run, that is, if we only use the minimum order solutions to this problem, the closed loop system is going to be unstable, and the given noise and plant uncertainty, it's unstable. So the system's blowing up, and when you look at the plot, it just just takes off. So I'm not even plotting it. When the robustness program is run, these are the results we get. Remember, we have uncertainty and we have noise. Okay. Now looking at this, I can see that the result is not perfect, but considering the fact that you have if you look at the noise here, there's quite a bit of noise on that signal, quite a bit of noise. And so notice that the overshoot and all those kinds of things don't really, they aren't really satisfied. But if you look at the control signal, notice the control signal is, at least it's not blowing up. It's trying to keep things in check. But of course, it's with the noise, it's like the controller is like, it's like riding a bucking bronco, right? It's the noise is doing whatever it does, and this, the controller is just trying to hang on, right? And trying to make it go. Basically, it's keeping it hovering around 1. So it's meandering, but at least it's hovering around 1. And so it's actually, maybe you could do better by increasing the order of the polynomials for involving V2. In other words, increase the order of V2. You could possibly do better. So that would be something to consider. Well, actually, I just went through and I tried increasing the order for robustness. V2 of order 10. I went to order 20, 200, 2000, and remarkably, I did not get much better. So there's no advantage of going to a larger order. This is really about as good as you can do, given the amount of noise that's available. I mean, the amount of noise that's hitting the system. This is about as good as you can do. So, but we have a way of at least looking at that, right? We have the tools to do this. Yes. So we now have covered the complete control design problem when we're trying to track a step input. We've looked at the robustness issues and we've looked at the performance issues. And now we have a unified way of dealing with both of those issues, and we have tools that can help us find solutions to these problems. Thanks for watching.